this is, I'm sorry, length is 2.1. Your capacitance is going to be 0.2 femtofarad. And I'm plotting the same thing with wire width. So visually it kind of looks okay because see it's encompassing. The model is kind of covering the data set. So far it's looking okay, but I don't know. The values looked okay. The plot is looking okay. Now let's try and predict some values, sample values, the way you would do in a product. This is how you would do it. I mean, so you've given it a wire length, and you're predicting the values. And now you would need all three of them to predict, and this is what is the input: wire length, wire width, and wire thickness. This is what is passed, and then the model is predicted and stored at predicted capacitance, and this is what we are printing here. Actual capacitance is this, predicted capacitance is this, and this is your difference, essentially the error. And this error, if you compare minus 16 to minus 18, 1%, 0%, under 10%, less than 0.1%, less than 0.1%, under 10%, under 10%, under 1%, under 1%, under 1%, and so on and so forth. So it looks good. Most of them were either 1 or 0. Now let's look at the error mean, and this is the main thing. For a regression, you would want to look at error mean and error distribution. So error mean 0, validation error mean is also 0. So training is much better than validation, and distribution is also good, 0.014. This is a reasonably good and tight distribution. And so now let's plot our errors. So this is our error plot. So this is wire length and this is prediction, I'm sorry, error. So the error, you see the pretty much most of the data set is close to 0. I like this visual. And same thing here. Most of the data set is close to 0 and kind of representative of your training set. So training set and validation set are very close in terms of results. And also the error is 0. And this is a sign for your good plot. Now, if you see the number of parameters that capacitance depends on, we are 3, and we took 3 parameters, right? So now if I want to plot I want to visualize the predicted model, the model that it's giving me. I'll have to plot somehow that in 4D. And the reason is you have 3 variables that are input, and the 4th one is your capacitance and is output. So the way you can use 4D plot is essentially draw a 3D plot and encode the 4th variable as a color. So what I'm doing here is using pretty well established technique to visualize 4D data in data science, whereby you have length on one axis, width on y-axis, and capacitance as a prediction in z-axis. Now thickness is represented as color. So the color variation you see is actually thickness variation. So you might have, let's say to pick 2 dots, which one of them is red, the other one is, let's say, yellow. For example, let's say the extreme one, right? These two. What that means is the darker one has more thickness, and the lighter one has less thickness. And so more thickness is giving you higher capacitance than less thickness, sort of is the trend. And this is what I would expect based on the visualization that we did before. So this is a good visualization exercise. I mean, 4D, I don't know if anybody has tried plotting that before. But this is one way to plot. The other, you can do 5D by including the size of these dots, whereas in color and the size, they become 2 additional dimensions. So you can actually visualize up to 5D in a 2D surface. Beyond that, there are other techniques, like especially for deep learning, people are using T-SNE and PCA to visualize in higher dimensions. I'm not going to cover that. So this is the end of the exercise. Now I have left a couple of exercises for you. I want you to, yeah, one thing actually pretty much everybody is missing here, did not notice, likely because they're not sharing it. You might have noticed that cost and accuracy of the results, it changes slightly from one session to the next. It's not going to be the same result if you run it again. So there is a reason for that, and the reason is there is randomization in our formulation, there is randomization in TensorFlow and NumPy. So every time you run the algorithm, it has that random effect. All you need to do is to provide the seed so that every time the same random numbers are picked. And the way you do that is by using these two these two random seed functions in the code before you start, and the exercise is for you to make sure that the results are reproducible by adding these two statements. And you can pick the seed of your choice. These two functions, tf set random seed and np random seed, they take an integer. So you can pass whatever you like. And second exercise is change the model capacitance to your liking and see how it changes your accuracy, and see if you can find a better than I did. And this is your optional exercise where wire load model is what it looks like. So this is what wire load model is. Has a resistance that we already did. So has resistance, has capacitance, and the third one that we did not do so far is fan out length. So this exercise is asking you to sort of complete this exercise, collect a sample of sample of a simple wire load model is shown below, and we are missing fan out length in the complete wire load model. Now collect a database or for fan out versus wire length on a signed off design. It could be very small data set, and use the regression to generate a machine learning model and add the table. And once you add this table, you will have the entire wire load model for your exercise. So this is what finishes the wire capacitance estimation, and we are going to stop here.
So shall we take some queries here?
Sure.